So last time we were talking about essentially how weather affects health. We also had that question that I said was kind of tricky. And afterwards, so I don't think the way that I explained it was perhaps not all that clear to many people. So afterwards, I sort of had I was talking to some students, and I had a couple sort of different explanations that maybe were more accessible. So let me just spend 1 minute trying to sort of get across the point that I was trying to convey in that exercise. So to sort of make the example hopefully as clear as possible, I had written up that regression equation on the board where somebody's lifespan is a function of whether or not they smoke, and then also whether or not they get lung cancer, and a bunch of other unobservable things that determine people's lifespans, which are captured by this epsilon I. And so the point was that in this situation, you don't want to control for whether or not somebody gets lung cancer if you're interested in the effect of smoking on somebody's longevity, because smoking itself causes lung cancer. So if you sort of control for lung cancer, then you're saying, well, what's the effect of smoking if somebody doesn't get lung cancer? But of course, one of the main pathways through which people die from smoking is through getting lung cancer. So there's sort of two other ways maybe to look at why you don't want to include lung cancer as an extra control in this. So normally you think, yeah, I want to include lung cancer because I know that, first of all, lung cancer is correlated with smoking, and second of all, lung cancer affects longevity, and therefore it seems like it has both of the properties that would make me want to include it as a potential control because it's correlated with the treatment and it affects the outcome. But the reason why you wouldn't want to do that in this case is, or a couple ways to look at why you wouldn't want to do that in this case are, first of all, so if you think about the effect of smoking on longevity, you can think of sort of different channels through which smoking might affect longevity, right? So one channel is you might get lung cancer from smoking. Another channel is that it might increase your blood pressure and then you might end up with like a stroke or heart attack from smoking. So there's different possible channels, and lung cancer is one of those channels. So you don't want to sort of control for the channel through which smoking is causing a decrease in longevity, because that channel represents part of the causal effect of smoking on longevity. So you don't want to sort of remove that causal effect. So that's one way to look at it. The other way to look at why you wouldn't want to include lung cancer as a regressor here, or as a control variable, if you've taken econometrics, then you're probably familiar with the term endogenous variables versus exogenous variables. So endogenous variables are variables that are basically determined by other variables in the system, so they're like in some sense outcomes. And so in the language of econometrics, lung cancer is an endogenous right-hand side variable. It's endogenous because it itself, if you wrote down system equations, lung cancer itself would be caused by whether or not somebody smokes. And we know that we don't want to put endogenous variables on the right-hand side, so on this side of our regressions. So if you have some econometrics background, then that's basically the explanation for why you wouldn't want to include lung cancer in this case. In the weather case we were talking about, basically the analog is, so now we're talking about longevity as a function of cold weather, so whether it's cold, and then whether or not you exercise, but whether or not you go out to exercise could itself be directly like causally affected by whether or not it's cold, because if it's like 0 degrees outside, then you really don't want to go exercise. So since whether or not you exercise is itself basically either a channel through which the cold weather could affect longevity, or you can think of it as being an endogenous variable, you don't want to have it on the right-hand side as a control variable. So that's just, that's sort of the thrust of where that question was trying to go, or what it was trying to demonstrate. Okay, so the basic result, like the first result in the paper that we discussed, is that warm days are contemporaneously related to mortality rates. So like on a day when it's very warm, we see that in fact there is a big spike in mortality rates, and cold days don't seem to display that contemporaneous relationship. But I said that that it turns out that when you sort of take into account the longer run impacts of a cold day or a hot day, that these relationships or these correlations basically reverse themselves. So there's two reasons why these non-contemporaneous effects are potentially different than the contemporaneous effects. So the contemporaneous effect, again, is on day 3 if it's really hot, then I see a spike in mortality on day 3. The non-contemporaneous effect would be something like on day 3 if it's really hot, how much does mortality increase on like day 10 or day 15 after potentially controlling for whether or not it happens to be hot on day 10 or day 15. So is there sort of like a lagged effect here? And there's two important reasons why we might expect there to be these lagged effects, and they kind of work in opposite directions. So one reason is this harvesting phenomenon that we discussed earlier when we were talking about air pollution. And with harvesting, basically what can happen is that we may overstate the impacts of extreme weather on mortality because the deaths on subsequent days are going to fall below the average death rate. So if you kind of think of it like in terms of a graph that shows you the effect. So on the x-axis here, what you have is basically days after the hot or the cold day occurs. So this is days following the extreme hot or extreme cold day. And then on the y-axis, you have some measure of the mortality rate. So here you have like 0 days. Maybe here you have, say, 2, 4, 6, 8, 10. And so if we're basically, let's see, it's a mortality rate effect. So if we're basically plotting the mortality rate effect as a function of how many days after the hot day or the cold day we're looking, then what you might expect to see with harvesting is something like the following. So say this is like the average rate. If there's an immediate contemporaneous effect, then on day 0, you'd see that perhaps you're estimating that on average the mortality rate is up here after a hot day because it's increased relative to the average. And then if there's harvesting, so there's sort of various possibilities here. If there's harvesting, then what that says is that what happened is essentially that there were some very weak people in the population, right? And when you had the really hot day, it sort of pulled up their, like they were kind of on the verge of expiring, and so it sort of pulls up their demise, unfortunately, by a couple weeks or something. Had the hot day not occurred, they would have lived longer, but it wouldn't have been a lot longer, right? Because they were already in pretty bad shape. So what that would imply is essentially you see the spike in mortality on the hot day, the first or second day, but then over time maybe the mortality rate actually falls like a little bit below the average rate, right? Because the phenomenon I just described basically said there are people who would have been dying, maybe 10 days out or 5 days out here. Now they're going to die the same day because it was very hot. But that means that, since they've already expired, basically their deaths will not appear 8 days later in the data as they otherwise would have if you hadn't had that hot day. So basically you can think of sort of like there's a bunch of people who without the hot day sort of would have died in these later days, and now their deaths are being pulled up a couple weeks or something to the current day when it happens to be really hot. So if there's harvesting going on, then this is kind of like what the time series pattern of the effects would potentially look like. But there's another potential phenomenon here that could go the opposite direction, which is that you could have some sort of delayed impacts. So if they're delayed impacts, then that actually, so the harvesting causes you to like overstate the impact, because if you just look at the contemporaneous effect, you say, oh wow, there's a big effect here, but you ignore the fact that in fact there's actually a sort of reduced mortality rate in the subsequent days, right? On the other hand, if there's delayed impacts, what that says is that maybe so the type of sort of the causal story in this case would be something like the following. So maybe it's like really hot today. Somebody ends up getting like a heart attack or a stroke or something because it's really hot, but they get taken to the hospital. They don't die immediately. Instead, maybe they die like 8 days later or something like that. Or in the cold weather case, you could have something like it's really cold. They go outside, they slip on some ice or something. They end up like breaking a bunch of bones. That doesn't immediately kill them, but it weakens them, and then they end up in the hospital and they get an infection and bad things happen and so forth. And so then, even though they didn't die that day because of the cold weather, they end up dying maybe 10 or 20 days later or something like that. So if that were the case, if that type of phenomenon were then again, of course, you would see this contemporaneous effect right here on the first day. But you might also then expect to see some sort of like delayed effect later on. So you could get something that looks sort of like this, where if you have a really hot day or a really cold day, there's a spike in mortality, and then mortality falls in the subsequent days, but it doesn't fall all the way back down to the average rate. It's still somewhat elevated here. And it could even be the case that you could get like a pattern where the initial mortality rate spike were like maybe somewhat moderate, but if a lot of the effect were coming through these delayed impacts, then you might actually see an increase in mortality in the subsequent days, and then eventually, of course, fall back down to average mortality rates. So this is like if you had an extreme cold day or something, and there's some initial spike, and then it actually increases over time because these delayed impacts are kicking in a few days later. So what they do in the paper to try to sort of get a handle on which of these two phenomena is operating, or whether both of them potentially are operating, is they estimate the correlation between mortality not just on the same day, or the correlation between mortality and heat waves not just on the same day, but also the relationship between mortality and whether it was hot like 1 day earlier, 2 days earlier, 3 days earlier, and so forth, all the way to like 30 days earlier. So now the thought experiment is not asking, if it's hot today, do we have higher mortality rates today? It's instead asking if it was hot 30 days ago, are mortality rates higher today? And I should also note that in all of these regressions, they're always like they're putting in basically all of these measures on the right-hand side of the regression. So what they're doing is they're modeling mortality today as a function of the weather today, the weather yesterday, the weather 2 days before, and so forth, all the way to the weather 30 days before. So this is basically controlling for the current weather, looking at looking at the effect of weather 30 days ago, right? Because if you don't control for the current weather, then if I tell you, well, it was hot like 2 weeks ago, you might say, well, heat waves can last a while, so maybe the reason that you see elevated mortality today is because it's hot today, because that tends to be correlated with it being hot 2 weeks ago, and then it's the heat today that's essentially generating the excess mortality today. But they're actually controlling for whether or not it's hot today. So you can think of it as like holding constant the current weather does having bad weather 2 weeks ago, or 3 weeks ago, 4 weeks ago seem to increase the mortality rate. And again, they're putting in these county and month fixed effects to basically just look at whether or not you get shocks to the weather relative to what it normally is in a given county during a given month. And so the basic, like the bottom line is that the cold days seem to display evidence of these delayed impacts. So it turns out that a cold day is correlated with increased deaths on subsequent days. And this is even true when you're controlling for the temperature on those subsequent days. So you're basically controlling for like the contemporaneous temperature. And so if you actually plot out what the function that I was kind of drawing up here looks like when they take it to the data, what you find is the following. So you can see actually the contemporaneous effect is close to zero. So like right at day zero, if it's very cold on day zero, you don't actually see much of a change in mortality. But within a couple of days here, you can see that mortality rates are elevated relative to the average. So basically the average rate for a given county in a given month is given by this line at zero, because everything's sort of being mean relative to its average. And so you can see the spike in mortality rates for, I'd say, the first, well, it's pretty pronounced for maybe the first 4 days after a cold day, and then it stays elevated for up to maybe 10 days or so after the cold day. And there isn't really evidence of harvesting here in the sense that you don't ever see the effect of the cold day going down below the average rate even 30 days out. Like in a few cases, it falls a little bit below that black line there, but for the most part, it's above there. So it turns out then that the cumulative impact of the cold days on mortality is greater than the contemporaneous impact. So that's like kind of a reversal of the last result, or the contemporaneous result. And then the hot days actually display evidence of harvesting. So it turns out hot days correlate with decreased deaths on subsequent days, again, even when you're controlling for the temperature on those subsequent days. So this one is not, like the evidence is not so strong. So you can see there is this initial spike in mortality, and it sort of sustains itself for like a couple days after the extreme hot day. And then it kind of drops down to around zero. So there's certainly not much evidence of like a delayed impact after about 3 days out or so. But actually it tends to be, so it's both above and below zero here, but it actually tends to be below zero more often than it's above zero. And at some points it's actually like below zero to a statistically significant degree. So these dotted lines are giving you some sense of like the precision of the estimates, but it's actually not the dotted lines don't represent a 95% confidence interval. It's actually, I guess we'll work out to like an 80% confidence interval because it's only plus or minus one standard error. But in some cases, like this point here, this would be statistically significantly different than zero or below zero. So overall, if anything, it seems like there's some harvesting going on with the hot days. And because of that, then the cumulative impact of the hot days on total mortality is less than the contemporaneous impact. But I should say, this cumulative impact is not that precisely estimated. Let's see.
Is there any reason why it's so quickly?
Why it's like jumping up and down?
Is it like really high mortality rate and then like the next day or so?
Yeah. No, that's a good question. I mean, so it does seem, so first of all, there's like a substantial amount of noise in the data. So some of this is just random noise. That being said, like it does seem to fluctuate pretty wildly. Like, at this point, if you sort of tested whether this effect here is different than the effect over there, you probably conclude that they were significantly different. Why that would be, though, is a good question. So, I mean, it almost seems like there's like a negative serial correlation here in the sense that it'll be like below zero one day and then above the next day and then below the following day and then above the day after that. And I don't know. That's a good question. I mean, it seems really unlikely that sort of the true relationship or the true like causal relationship here could be such that there's always going to be like lower mortality 4 days out, or whatever it's like 3 days out and then higher 4 days and then lower 5 days. In the data itself, it may be the case that there's sort of just a stock of vulnerable people, and so if a whole bunch of them die on one day, then there's essentially less of them that are going to be around to die the next day. But yeah, overall, I'm not quite sure exactly why it's sort of is displaying that sawtooth pattern. It's a good question, then. So then if they put together like essentially both of these estimates, they can basically plot out what the effect of different daily temperatures is, both contemporaneously. So that's the line with the circles in it. It might be kind of hard to see, so that's this line here. And then they can also plot out sort of the cumulative, they call it the cumulative dynamic effect, but what it's basically doing is adding up all of the effects from the contemporaneous effect all the way out to like 30 days out. So it's kind of just like, you can think of it essentially integrating under or over the curves that they plotted out in those two graphs there. And so what this is showing graphically is essentially what I told you earlier, that heat seems to have a big contemporaneous effect, but a relatively modest cumulative effect, whereas the cold seems to have a modest contemporaneous effect and a larger cumulative effect. So this is saying like 0 means there's no effect, so this is saying like a daily average temperature of 10 degrees or 10 to 20 degrees, 20 to 30 degrees, and so forth. There's no contemporaneous effect on mortality, so you don't see a spike in mortality on those particular days. It's only when you get up to basically 70, 80, or 80, 90, 90 above, so these are like pretty hot days, that you see contemporaneous mortality starting to increase. The cumulative dynamic effect, though, basically shows you the opposite pattern, right? So that if you kind of look at all of the effects, both contemporaneous effect and adding up all the effects after 30 days out, then you can see a pretty big effect there when it's really cold, so like less than 10 degrees average daily temperature, probably means it got well below 0 degrees Fahrenheit, not just centigrade, but 0 degrees Fahrenheit during that day. So there you can see that then when you add up the cumulative total effect on mortality of such a day, it tends to be very high relative to the average, and then it declines, so still above average, basically all the way up to like 40 or 50 degrees. So an average temperature of 40 or 50 degrees is probably about as cold as it gets in the Bay Area, but certainly in like the Northeast and other places like that, it can get well down into this range over here. And then when you get all the way out to the very hot days, you actually don't see much of a cumulative effect. So essentially that contemporaneous effect that you're seeing in this line here is being more or less offset by a decrease in deaths on following days, and that's why the cumulative effect isn't too large there. So the last kind of the last thing that they look at, or the last calculation that they do to try to give you a takeaway from the paper, is to look at what they think happened, or what the effects of migration to warmer states have been on mortality rates in the U.S. So there's sort of this long-term trend that people are moving away from what we call the Rust Belt, so like Michigan and Ohio and places like that tend to be very cold, and they're moving more towards like sort of south and the southwest and so forth. So places like Arizona and Florida and Texas and so forth are gaining a lot of population. And so they argue that their estimates suggest that that type of migration has actually reduced mortality rates to some degree, because we know that their estimates say that the cumulative effect of the cold days on mortality is much larger than the cumulative effect of hot days. And so if you move from a cold climate to a hot climate, then you could expect that you could see some improvement in mortality. And there's a back of the envelope calculation is that migration to warmer climates could explain perhaps as much as 5% of the 30-year change in mortality. So if we look at like mortality in the U.S. population, people life expectancies are increasing, so mortality per person, like age-adjusted mortality per person, is decreasing over time. And so if they calculate how much mortality has decreased in the last 30 years, and then try to figure out how much of that was due to migration to warmer climates, they guess it's probably about 5%. Now, of course, the other question that you might have is, well, how does this potentially interact with like climate change or something? So on the one hand, it's not totally clear. So climate's getting warmer, their estimates suggest that that's not necessarily bad, especially if you can avoid some of the extreme cold days. On the other hand, if the climate's getting more variable, then even as it gets warmer, you still might end up with as many or potentially even more extreme cold days. So it's not totally clear what the net impact would be. That said, they don't really, they sort of don't try to go there. So you could, in theory, take like these climate model forecasts and then try to back out or combine that with their estimates and figure out what the potential impacts on U.S. mortality rates would be. But I think there's enough uncertainty in exactly what's going to happen with climate that they didn't really want to engage in that type of exercise. Okay, so now let's see. Okay, so the next thing that I want to talk about is basically sort of obesity and like the built environment, things that affect obesity. So we're kind of transitioning away from, this isn't sort of like a purely environmental topic. I mean, it is about the environment, but it's not so clear that it necessarily involves externalities. That being said, I think it is sort of part of the health production function. So remember, we're talking about the health production function, we're basically saying, look, there's different ways that society can potentially produce improvements in population health and like lower mortality and increase safety and so forth, right? And so one way is that you might invest in sort of improving environmental amenities, so like reducing air pollution, trying to mitigate climate change, things like that. Another way, of course, is you can invest in like medical technology, which is what we'll spend basically the last month of the course talking about. So for most of November, we'll be talking about sort of how the healthcare system works. But there are also other sort of population level type investments that you can make. So certainly like, and if you look at sort of what the major what the sort of major driving forces behind improved longevity, so increased lifespans are, they tend to be the sort of more population level investments, so like proper sanitation and clean water and sort of general public health investments. Now I think in the U.S., so two of the leading causes of what we call premature death at this point are, first of all, smoking still. So the smoking rate has declined significantly over the past few decades, but it's still one of the leading, or basically the leading cause of premature death. But the sort of second leading cause I think these days is obesity, and that's something that at the current time, we don't really have sort of clinical ways to treat. I mean, you can imagine that they may eventually come up with some sort of drug or something that has relatively low risks and allows you to just lose weight. And in extreme cases, they do have things like bariatric surgery. But right now, it's sort of more about trying to modify the environment that people live in to basically encourage them to exercise more and eat less and so forth. And so in that context, I think it is kind of an important thing to look at. Now, in terms of the actual papers we're going to look at, so we'll look at one paper that I wrote with one of my friends from grad school, which looks at restaurants and obesity. And I think we'll also talk about another paper that's also sort of in the restaurant vein that looks at like these food or these calorie posting laws and obesity. And then I'll briefly discuss some of the results involving other policies that have been tested, like soda taxes and so forth. And the takeaway from most of these studies is that like it's really hard to come up with interventions that cause people to lose weight. And I think there's sort of a good economic reason for that. We'll talk about that later. So I guess in the last, let me start talking about the research that I did. And then at some point I'll also we'll watch maybe like a 8 or 10 minute clip from Super Size Me. I don't know how many of you have seen that movie, but that's sort of like that is what we would call an extreme sort of natural experiment that tests what happens when you expose yourself to an inordinate amount of fast food. The results generally are not pretty. And then we'll talk also about like the calorie posting stuff and so forth. But I think maybe we'll watch the Super Size Me thing on Friday since we only have like 10 minutes today. Okay, so just to sort of give you some background, obesity is widely recognized as this like emerging public health threat.